we're going to just go over the workbook pages. And additionally, I was going to start talking about some of the problems from the upcoming homework on graphs of rational functions, because guessing as you might have noticed already, the homework is a little bit of a hassle. There's a lot of parts to them. So I might need additional time to work out some of the problems that may be considered tricky or out of the scope of the notes that I covered on the subject. So let's just go ahead and jump right into the workbook pages. And since there's only a few of you, I'll check back periodically and see how you're all keeping up with everything. So let's see. So sharing, recording, cool. So I'm going to start off with the workbook assignment. So really, you're watching this at this point, might have turned it in already or not. If you turned it in and you see that what I'm providing is different than what you submitted, you're welcome to resubmit it. As long as you submit it by tonight, since the workbook assignment is due tonight at 11:59 p.m. So start off with page 15. And really this is, start off with problem 1, which problem 1 says construct the polynomial given a certain amount of information. And so with part A, it starts off giving us these zeros of -16 and 7, and it also gives us a degree of 2. So the degree of 2 is just saying if you added up all the exponents of the factors, then you would get 2. It's kind of a redundant thing here, so the degree doesn't really matter. More so it's the zeros. So if we make a function out of this, that means we need some function notation, f of x, and hopefully you recall for each 0, you use its opposite number to construct a various factor. And as long as you do that, this is all you have to do for it. It's nothing too engaged. So you might notice that the exponents, so this is the answer. So if you have this, you're perfectly fine. You may notice that the exponents are both 1, and by adding those exponents together, or those multiplicities really, if you add them together, you get 2, which matches the degree. Which again is redundant, but if you like to know why everything works the way it does, then that's precisely why. Oh, wait, move on to part B. Part B gives us a somewhat similar problem. They give us a 0 of 3, but then they immediately tell us what its multiplicity is. Tell us the multiplicity of 3 is 2, which means the exponent of the factor corresponding to 3 will be 2. And 0 multiplicity of 2. Or wait, I'm mixing up 2 of them. I'm sorry. My fault. Let's try that again. 3 multiplicity 2, and then -10. Yeah, sorry about that. -10 multiplicity 4, and then a degree of 6. That's what I meant. Okay, cool. So same idea. For each 0, we know what factors or what the initial structure is. So one of the zeros said was 3. So naturally, one of the factors is x minus 3. But then it immediately goes on to say that the multiplicity of that factor, which is just the exponent, is 2. So guess what goes as the exponent? It's 2. And negative 10, we have x plus 10, because that's our next 0, and it says that the exponent is 4. So that's really it. So imagine this probably didn't trip up too many people, but just in case, here it is. And so we'll move on to part C as well. So part C will give us a bit of information, zeros of negative 11 with a multiplicity 3, then 0 with a multiplicity of 2. And they tell us the degree is 5. Which again, the degree at the end just says if you add up all the exponents, you're going to get, well, that particular number. So you may notice in part B, the 2 exponents were 2 and 4. Add those together, you just get 6. And lo and behold, the degree of that last part is 6. Here, nothing too crazy. So it's a function, so I'm going to set up the f of x notation. One of the zeros is negative 11 with a multiplicity of 3. So the factor is x plus 11, and the exponent is 3. That's it. And now the next one is 0, which sometimes trips people up with a multiplicity of 2. So really, if you want, you can think about this as x minus 0 with an exponent of 2. This one tends to trip up a few people, but you can use 0. It doesn't mean that this is the, I want to say that MyMathLab would technically accept this, but you never know with MyMathLab. So that's why you can be safe and simplify this slightly, because of course subtracting by 0 doesn't really do anything. So really we can simplify this, and I'm also going to move this to the front as more of a stylistic thing. So x minus 0 is just x, and so that's x squared. And then I'll put the x plus 11 to the third. And that would definitively be something MyMathLab would accept. Or if the x squared was not in the front or in the back, it means the same thing. It's just a math. It's a math formatting thing, but not a big deal. So hopefully problem 1 wasn't too bad. I'd imagine that didn't trip too many people up, but there it is just in case. But, let's keep going. Move on to problem 2. And it says graph this function. And it says graph it by finding the power function and behavior intercepts and behavior near each x-intercept. So this one is more pertinent to those problems where you have to graph based off of various touching and crossing behavior, find the power function and behavior and all that stuff. So if anything, the power function, remember, I mentioned this before, the power function is a very important function. It tells you a lot about what's going on with the problem. It tells you the degree, the max number of turning points. It tells you the end behavior, so virtually the shape. Gives you a lot of information. So if we started off by finding the power function, we find this, remember, we find this using term domination, this idea of term domination. So anything adding or subtracting each other, those are now in competition with one another. And we're going to pick the more dominant of that addition. So -1/2 isn't adding or subtracting to anything, so it's fine. X plus 1, that is an addition, and the x is superior to the 1. So I will drop down an x, and then for the next one, x minus 1 squared. X dominates the -1, but there is a square associated to it. So that's why I will drop down the square. And then next one, same idea. X minus 2, the x dominates the 2, so I just drop down an x. And then we bring everything together. -1/2, what is it, x to the 4th. And that would be the power function, x to the 4th. Which immediately tells us actually a lot of information. So the reason why the power function is so important is because we can immediately determine that the degree is 4. Number of turning points has to be 3 then. And the problem isn't asking for this. I'm trying to help show why the power function is so important. All the immediate corollary results that follow from finding this. So this would be 3. Hopefully you remember the shapes, the 4 various shapes. So there's a negative number in the front and there's an even exponent, which means that the shape would take on somewhat of this feel, as we'll keep in mind later. This is more so the end behavior. So it helps answer that question. So suppose if you want to be technical, you'll just trim off the inside part since it's end behavior. There could be some weird stuff going on in the middle, but the ends are going to go straight down like that. But in any case, that's why the power function is so important. We just obtained a lot of information about the shape and the characteristic of the function as a whole by breaking it down to its most dominant terms. So from here, let's see. So from here, scroll down a little bit. So what else does it want? It wants intercepts as well. So it also wants the intercepts. Now the y-intercept, remember there's 2 intercepts. We'll start off with the y-intercept. Doesn't matter which one you start off with. Set x equal to 0. So now we have -1/2, 0 plus 1, 0 minus 1 squared, 0 minus 2. And so if you multiply all of that out, you get through all of it in your calculator, it doesn't matter. Probably get +1. Let's see, we have a 1, -1 squared is +1, -2 times that is +1. So we plug in 0 for x, we get 1 for y. So that's the y-intercept. X-intercept, we set y equal to 0. And this one's actually easier because now that we have a factored form, each factor is going to give us a different x-intercept, which are also zeros. So hopefully you remember that interchangeable terminology. X-intercepts are simultaneously the zeros. It means the same exact thing. It's just they use different wording for different contexts. So here -1, here we get +1, and here we get +2. Each factor gives us a different zero, or in other words, each factor gives us a different x-intercept. So for each one of those, so I'll start off with -1, and that was when we plugged 0 in for y. And then there's another one for +1, we plugged in 0 for y. Another one was 2, we plugged in 0 for y. So we have a bunch of intercepts. So now the last thing we have to determine is the behavior. It's the behavior at each value. So remember, the behavior is something we find by viewing the multiplicities of each factor. And we can view that right here. Since there's an understood exponent of 1 for those two factors that I just wrote in blue. Crosses for the first one because the exponent is odd, and then touches for this middle one at 1 because the exponent is even, and then crosses at x is equal to 2 because the exponent is 1. So the way we would graph this, so again, normally MyMathLab will pretty much facilitate this whole process for you. But if you didn't have MyMathLab, how would you proceed? And so let's go ahead. Okay, so let's go ahead and plot all these intercepts that we have. Definitive points on the graph. 0, 1, -1, 0, 1, 0, 2, 0. That would be the first step. And then we know the end behavior. It's the shape up here. So if anything, we know what the ends look like. It would be coming upwards. So we know what the end behavior is like. And now the last thing we have to do is figure out crossing and touching. This value on the far left, that's crossing, because that corresponds to x is equal to -1. So this would cross through and then hit this point. And then it has to go down to hit the next point, and we have to figure out, so what does it do at that next point? Does it cross or touch? The next point touches. So that means instead of crossing through, it'll just bounce right off. But then it has to hit this next point, so that's why I'm arcing it back down. So at that next point, we said it crosses. Which makes sense, because once it crosses, then it can come join the segment down here. So notice it doesn't really look parabolic, but that's not what end behavior necessarily implies. End behavior doesn't speak for the middle segment of the graph, it speaks for the end part, hence the end behavior. But ultimately, this is how you would graph one of these by hand. Generally, my math lab will give you a multiple choice option, which is very generous, because if you didn't have that, you would have to construct it by hand like this. So I think your primary responsibility would be to choose this graph in relation to a bunch of, not correct graphs and state that as your answer for the graph of the function. And if you haven't started the homework on the graphs of rational functions, one second. The lights, okay. The lights go out sometimes, so if that happens, I might have to get its attention. But other than that, suppose let's move on to page 17. And as I was saying, if you have not started the homework on graphs of rational functions, then this is pretty much what you can expect, this series of steps here. So they're not the most, I guess they're gratuitous problems. They have a lot of parts, they take a while, but just to give you an idea of what to expect. But other than that, I'll move on to the other part of the workbook assignment. Which was page 17, I assigned a few. So let's go ahead and look at number 1 from page 17. So I think in the last one I said that was a rational function. It's not a rational function, it's a polynomial function, so that's my mistake. This is a rational function because this is, well, generally rational functions are comprised of a polynomial divided by a polynomial. Hence why it's very natural to talk about rational functions after we talk about polynomial functions. So rational functions, they're pretty much the fractional form of polynomials. They're when polynomials are over other polynomials. And so this is what your homework will primarily deal with polynomials and fractions with one another, or ratios of polynomials, in other words. And so with this problem, it starts off by asking for the domain. Now, a rule that you just need to remember is that the domain of a rational number means you set the denominator not equal to 0, and you solve for x. And this is going to be pretty characteristic throughout this whole section. It's going to be very characteristic because rational functions have fractions. Fractions have denominators. You set the denominator not equal to 0 to figure out the domain. As long as you remember that, then this is perfectly fine. And at least on the workbook, you can leave you can leave it as an inequality like this. I think on my math lab, they allow you to leave it as an inequality as well. I don't think they make you use interval notation, but correct me if I'm wrong, if I am wrong on that. But other than that, let's keep going. So that's the domain. Let's also find the intercepts. The problem wants us to find the intercepts. So there's two intercepts. I'll just start off with the x-intercept. Doesn't matter. X-intercept, we set y equal to 0. And so when we set y equal to 0, we're setting the whole fraction equal to 0. And the first thing we do, well, we can cross multiply or multiply both sides by the LCD. It does the same exact thing. Which gives us exactly 0 times 3 plus x is equal to 3x plus 6, but 0 times anything is 0. And then we can pretty simply solve for x. So we get that x is -2, which means that the intercept is -2 comma 0. And additionally, we can go ahead and determine the y-intercept. So this requires us to set all the x's equal to 0. So 3 times 0 plus 6 over 3 plus 0. And so that's just 6 over 3, which is +2. So that gives us one more intercept. Wait, that is definitely wrong. 100% wrong. 0 goes first, and then 2. There we go. All right, so we found the domain, we found the intercepts, and we found the, and we're going to find the equations of the asymptotes. So this is primarily what distinguishes rational functions from polynomial functions. Polynomial functions don't have fractions, which means they're not going to, well, they don't have fractions, they don't have any square roots. Polynomials are pretty basic functions for the most part, which means that their domains are all real numbers. So they don't really have these things called asymptotes. Asymptotes, though, those act as barriers. Barriers happen really whenever you have fractions. So when you start having fractions lurking around, then you have asymptotes. And so these asymptotes represent restrictions that you may have. So let's find these asymptotes, these so-called asymptotes, and figure out the process for doing this. So there's two asymptotes, just like how there's two intercepts, there's two asymptotes. There's a horizontal asymptote and a vertical one. We'll start off with horizontal because I'm writing it down first. So the horizontal asymptote, the idea here is, so hopefully you remember the criteria for the horizontal asymptote. It has to deal with the degree of the numerator and the denominator. So I'm just going to go ahead and rewrite the function. Maybe not right there. I'm going to rewrite the function over here, just so we can look at it. So the horizontal asymptote deals with comparing the degree of the numerator and the denominator. So the degree, you have to figure out the degree of the numerator and the denominator. And remember, the degree is the exponent of the highest term. So for the numerator, the 3x plus 6, the degree is 1 because it corresponds to the x, which has an exponent of 1. So that's the highest exponent there. And same with the denominator. The denominator does not have, or the denominator is not in standard form. So don't be fooled and think that the highest term is 3. So hopefully you remember the criteria for the horizontal asymptote. Since the degree of the numerator is equal to the degree of the denominator, horizontal asymptote so whether you are going to watch this video or the video on the graphs of rational functions or otherwise, I list 3 criteria, and when these are both equal, it's the ratio of the leading coefficients. Now, this may be misleading. This may be misleading. This may not even make any sense right now. The idea of this, the leading coefficients are coefficients mean the number in front of the variable. That's all coefficient means. And when it says leading, it means if you put each polynomial in standard form, what is the number in the very front? That's it. You may notice that our problem over here on the left, the numerator is in standard form, which means that the leading coefficient, the number in front, just be 3. So if anything, that gives us an idea for the horizontal asymptote, which I'll denote HA. Normally, this is a y value. So it's a ratio, which means a fraction. So I'm using 3 because of the 3 I boxed in on the left, what is in the bottom. Now the denominator is not in standard form because the 3 is inferior in comparison to the x. So by simply switching to put all of the exponents in descending order, x plus 3 is now the standard form of that polynomial. And from there, we can determine the leading coefficient. So the leading coefficient was not 3 for the denominator. The leading coefficient is understood to be 1. So that's why the horizontal asymptote here is 3. So if you have not watched the video on graphs of rational functions, then this is, you will be seeing this idea again in that video. So this is a nice, I guess, introduction to some of the themes that you will see in that video. Because we do not deal with asymptotes for the polynomial section. Asymptotes are specifically a rational function thing. So if anything, this tells us the horizontal asymptote. Horizontal goes left and right. So it means that you would have one of those red dotted lines, or just, well, it doesn't have to be red. You would just have a dotted barrier at y is equal to 3. And that makes sense left to right because that's how horizontal works. So we'll remember that. In fact, if we want to go ahead and start thinking about our graph a little bit, let's see, I think in your workbook it goes by twos. So I'll do this by twos. So it's 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. We can go ahead and start plotting the intercepts. And we just figured out that the horizontal asymptote, y is equal to 3. So that means at 3, we're going to have one of these dotted lines. Just means a barrier. So we're slowly building the graph. So we'll scroll, let's go ahead and scroll back down. We'll scroll back up to the graph in a bit here, because there's still another type of asymptote defined. There's also the vertical asymptote. So let's put this over here. In fact, let's do this. So the vertical asymptote generally, the vertical asymptote corresponds to whatever x's give you 0 in the denominator. And I do have to preface this with a technicality that there is a certain word that they use. You might see the word, if you use help me solve this, you might see them use the wording a non-removable discontinuity. It sounds very technical. Now, what does that mean for something? So a discontinuity, for all intent and purposes, we're going to view that as vertical asymptotes in a sense. But there is some exception. So I technically can't just say that your vertical asymptote is whatever you put for your domain. Because I'm trying to think of an example you might have. So perhaps if you're more so interested in how everything works from a fundamental perspective, in fact, let me just write out a few of these. So if you had a problem like here on the bottom left, and we'll get back to the vertical asymptote thing in a bit. So let's pretend like this was a whole new problem over here. So if you looked at this problem, you would say that the domain is x cannot equal -1 or -3, because that comes from what happens, what makes those two factors equal to 0. And equaling 0 in the denominator is bad. So those two numbers would definitely be excluded from the domain. Now, the rule of thumb I wanted to give is that the vertical asymptotes I'm going to write this in red because it's not true, would just directly be whatever your domain wasn't. Notice that's normally the case 95% of the time, that your domain will just be recycled. Notice all I did was change the equal sign. It went from a not equal sign to an equal sign. And the problem we're working on, we found in the very beginning that the domain was x cannot equal to -3. And in this problem, it would be true. Well, you would think it might be true that this would also be a vertical asymptote. But there's this idea, this isn't necessarily true. There's this idea of a removable discontinuity. And so what does that mean? Notice in the problem that I wrote down here, the x plus 1's cancel. So guess what we just did with the x plus 1? We removed it. So that's a removable discontinuity. And so what happens with a removable discontinuity, it means for that value you just removed the asymptote. So that's why the true vertical asymptote here, that would stem from whatever number is left over. That cannot be removed. It's a non-removable discontinuity. So notice I'm only taking one of the answers. The other one, I removed it, so it cannot be an asymptote. So let's bring that back to the problem at hand. So the problem we had was 3x plus 6 over x plus 3. Now we want to see, before we figure out the vertical asymptotes, are there any removable discontinuities? And I guess x plus 3 or 3 plus x, it doesn't matter. They're both the same thing. I'm just going off of this simplified form. Well, let's see. So is the problem, as you'll notice in the homework, I think one of the first parts it asks you is put the rational function in a factored form. And this would be the factored form. Notice I factored the numerator because both terms had a 3 in common. And notice there's no removable discontinuities. There's no factor on the top and the bottom that we could simply cancel out. So that means our vertical asymptote would simply be that domain that we had from before. Notice it's exactly the domain that we had. The domain said that x was not equal to -3. Here we're just switching out the sign. Instead of not equal, it's now equal, because asymptotes want to know the restrictions. But what this tells us, so this is a vertical asymptote, which is up and down. And so that tells us that we would have a dotted line here at x is equal to -3. And again, you won't have to know this problem too religiously, as my math lab will relegate the graphs of these to simple multiple choice. And it would just be your responsibility to, pick them out, or pick the correct one from the other ones based off of process of elimination. So besides for that, that's really all we have in terms of characteristics of the graph. And from here, the final thing to keep in mind is to figure out how to graph this thing. Now, if anything, all we have two points that have to connect, and we have these asymptotes, which are these barriers that the graph will get very, very close to, but never touch. So we have to trace along them, just like this. So you have to do that with asymptotes. You can't really cross them. You have to just simply trace right next to them. And that's really all you can do. But we're really not done yet, because this graph actually happens. We didn't draw anything to the left of the graph. We drew everything to the right of that vertical asymptote, not to the left. And really what ends up happening, as again, this is relegated to multiple choice, there's another part of the graph that you're not able to see immediately because you didn't have any, there's no way to get any intercepts in that region to be able to trace it out. But your multiple choice will show you this. And you can always just pick a test point to verify this. If you picked, so let's see, for example, this is -6. And if you plugged in -6 for x's into your function, let's see, if you plug in -6, it's -18, -12 over, is that -3? That's +6. So you would get 2, 4. So my graph's not very good. You would technically get a point up here, but you get the idea. But this would be the graph. And again, this is, as you all probably know, the workbook pages are more difficult than the homework questions. But if you had to do all this by hand, if this was a paper class, then you would have to construct all of this by hand using the aforementioned processes. So that's how you would do problem 1, with a little bit of a description for how you find asymptotes and all that stuff, and just stuff about discontinuities, which I talk about in the video. So besides for that, let's go ahead and do, let's go ahead and do the last workbook problem. And this one says that g of x is equal to -1 over x plus 2 squared minus 3. And it wants us to follow the same steps, use the same criteria. So it starts off wanting us to find the domain. So the domain here, we do have a rational function. So the domain of a rational function is you set the denominator not equal to 0. Because the denominator is x plus 2 squared, so we just set that not equal to 0. To get x plus 2 by itself and get rid of that square, we can square root both sides. We can simply square root both sides. One second. Sorry about that. So yeah, we can square root both sides. Square root of 0 is just 0, so simply have x plus 2 not equal to 0 now. And from there, it's just x is not equal to -2. So that is the domain. And as I mentioned earlier, provided as long as you don't have a removable discontinuity, and this will also represent the vertical asymptote, or this will heavily contribute towards the vertical asymptote. So in other words, we can really look at this in one of two ways, but as long as we cannot cancel out the x plus 2, then this would be the vertical asymptote. So we can go ahead and knock this out real quickly. So notice the domain and the vertical asymptote are very much closely related. Notice I was able to just derive one from the other by simply changing a sign. And this is all contingent upon being able to remove the discontinuity or not. But again, this association will legitimately happen 99% of the time. The mathematician in me wants to inform everyone of the additional 1% case that I explained above, but 99% of the time, that association that I just connected with the red arrows, that will happen, like I said, 99% of the time. So that's the domain, and we got the vertical asymptote out of it. So we'll keep that in mind. Let's look at the intercepts. So there's two intercepts. So x-intercepts at y equal to 0. So 0 is equal to negative 1 over x plus 2 squared minus 3. We need to add 3 on both sides. Okay, 3 is equal to negative 1 over x plus 2 quantity squared. And now we can cross multiply or multiply both sides by x plus 2 squared. It doesn't matter. So this would be 3 times x plus 2 squared is equal to negative 1. Which means you would have to FOIL. Again, workbook problems, they're more difficult than the actual homework problems, so bear with me. So this is 3 times x squared plus 4x plus 4 after you FOIL. And then you just simply distribute the 3. And we can add 1 on both sides to get plus 13. Which we get a quadratic. So this one's not a very fun one to find. And again, in my math lab, it's going to relegate this problem to a transformation problem. So it'll probably be a little bit easier when you see problems like this. As you'll see in my video, or as I'll most likely talk about on Wednesday as well, Wednesday's class period. But if you go ahead and apply, I'm just going to apply the quadratic formula right quick to this. You can also use the AC method, but I'm not going to focus on the factorization. I'm going to trust that everyone knows how to do that by now. And actually, what you end up getting that we are not able to obtain a particular value for the x-intercept. So we do not even have an x-intercept. So there's no x-intercept. All that work was for nothing. Because we got a negative underneath the square root, which is not good. So if you tried to factor this, you would never find a factorization. And when you use the quadratic formula, you would run into this issue. And so the y-intercept, we set x equal to 0. So this one should be much easier to find. So this is negative 1 over, now 0 plus 2, quantity squared, minus 3, which is negative 1 over 4, minus 3. And that, as a simplified fraction, improper fraction, is negative 13 over 4. So we have a y-intercept. Just like that. Now, finally, it goes on to ask us about the asymptotes. And here, we already have one of the asymptotes. We get it directly from the domain pretty much 99% of the time. So there's only one more, the horizontal. So the horizontal requires a rational function. We do have a rational function aspect. This is the rational function. The minus 3 we're going to ignore for now because it is not part of the rational function. So the rational function part, we need to figure out the degree of the numerator and the denominator. The degree of the numerator is 0 because there's no x, and the degree of the denominator is 2. So remember, when from these criteria for the horizontal asymptote, since the degree of the numerator is smaller, the degree of the numerator is less than the degree of the denominator, implies the horizontal asymptote is x is equal, or sorry, y is equal to 0, always, just 0 by default. The only problem is, so horizontal goes left and right, but remember that minus 3 we left off? That's what minus 3 does in a transformative sense. It shifts everything down 3. And this is where the transformation part comes into play. Again, my math lab relegates this to multiple choice for various graphs, but if you want to know about how these graphs are derivated, this is sort of the process how. So really the horizontal asymptote is y is equal to negative 3. So a very nuanced problem indeed. So if we start to think about the graph of this, So again, I'll go by increments of 2, 2, 4. So we found a vertical asymptote of 2. Actually, that should be -2, my fault. It should be -2. It's the same value. I don't know why I changed it. It's my fault. So a vertical asymptote, vertical up and down, of -2. We found a horizontal asymptote of -3. And we found one intercept that was 0, -13/4. And to give us an idea of the decimal, so we can make sure the point goes in the right spot, it's -3.25, I believe. So that would go a little bit past the asymptote. So that gives us an idea to trace here along the asymptotes. And it turns out, again, you don't really see this unless you plug in a test point, say, plug in -4. You would end up getting an answer that's down here. So you'd realize that the graph also goes down here on this side as well. So these are the workbook problems. And by the amount of time it took just to explain the 2 problems from page 17, this shows that the upcoming homework on graphs of rational functions is not a joke. You should not wait until the last minute to do this homework. But as these excess of parts will be requested by my math lab for you to find. So other than that, that's really all I have in terms of the workbook. And I suppose if, okay, Shannon, let me finish my little speech and then I'll read what you have. So yeah, so that finishes up everything with the workbook. And I suppose since there's 10 minutes left, I can ask about any specific problems you may have. But if you don't have any specific problems, then that's really all I have for today. And I'll talk about graphs of rational functions on Wednesday's class period, where that homework will be due that night. So, all right. So Shannon, let's see. -4x squared. 4 minus 5x squared. Determine the power function. So let's see. It's term dominance.